So how do we work smart in Corning? We did our first smart manufacturing test bed. We got started in July of last year. And so let me just tell you a little bit about that. This test bed is on a product that Corning's working on in a process. And just for simple understanding, we have glass that comes into this process, and we do some manipulation of that glass, and then it goes to another process step, and we do some additional manipulation of the glass, and then we have a final inspection. Well, the problem is that that first process doesn't have an inspection, doesn't have a measurement, doesn't have a way for me to monitor how is process number one performing. And we are working on sensors to do that, but we don't have it yet. And what we need to do is really challenging. So we're looking at, we have a final inspection that has the throughput capability for manufacturing. So how do we leverage monitoring those key process input variables from each of the processes, monitoring what we can in terms of the in-process measurements for each of those processes, and building a model that says, when I run my processes in this way, this is when I produce product that meets the customer's expectations. And so we've got to build modeling to essentially be able to have a controllable process, have a high-yielding process, and as you can see here, it may even involve a manufacturing strategy that this product isn't completed under one roof. It may be completed in two separate locations. And so now this is where cyber-physical systems start to close that gap between locations so that we can take a decoupled process in the physical world and make it coupled in the digital world. So just for illustration purposes, talking basketball. We have something that we call integrated process design and for process control, and this is something that's in literature. But what you need to do is you need to get the subject matter experts together across the organization, and you need to identify what defines critical to quality attributes. In this case, it would be free throws made, not free throws missed. And you need to have each of the materials, process area, controls, measurements people come together and say, for those CTQs, what are the key process input variables that drive the performance of them? And the more mature your manufacturing is, the more that this chart is filled out and you know. The earlier you are in your process life cycle, the unknowns are a lot greater. And so what you do is you say there's as I say, there's 100 things that can be measured, but you don't have the money to measure all 100. So where do you get started? And so you leverage that subject matter expertise to prioritize and say, this is what we believe based on our education, based on our experience, based on the data we have so far, are the key process input variables that we need to monitor. And you do your design of experiments and you understand how much of the variation am I explaining based on what I can measure. But when you start thinking about critical to quality, even in research and development, it gets the team focused on the game that you're playing and what defines success. And that's really important because now people are working on a common goal. Instead of, well, I'm trying to improve this, well, I'm trying to improve that. We all have to be working in concert with one another to improve each of them in an organized way. And so through the, I'll say about 4 months of 2016, we added several measurements. We added measurements that went from only being able to measure 15% of the attributes to being able to measure 100% of the attributes. And for those that have worked in I'll say processing and processes, averages can tell you something, but there's a lot they don't tell you. Standard deviations tell you something, but there's a lot they don't tell you. So for example, in the top left corner, there are essentially there's a map of where are my averages higher and where are my averages lower. And this starts to be really critical information when you're trying to understand what's driving performance of my process. And when you have the data, then you can look at it in ways that tell you more. And you learn that, hey, actually, I need more sensors in this process in order to be able to characterize what's going on in the process, because one sensor doesn't tell me what's happening in terms of this map that you see in the top left corner. And then you go back to first principles, you design models that represent what you're doing, you validate those models with the data you're getting, and you essentially write your equations that define your process behavior. Oops. So with taking this approach of getting everyone focused on the goal and having appropriate sensors, having the data systems to support their learning from those sensors, we were able to drive our attributes to improvement in just 4 short months. And actually, it was less than that. It was probably more like 2.5. What does this mean? This means that the team was able to focus, improve the process, and we know that we're not quite there yet. In early stage, there's a lot of times the customer can't tell you what the spec is. And I call it drawing the line in the sand. You got to start someplace. You got to start shooting for something. And when you start shooting for something, you can get the team to focus to improve. And the reason it's a line in the sand is it's our best knowledge based on working with the customer, based on understanding what the customer's trying to do. And if you didn't guess right, nice thing about drawing a line in the sand is you can wipe that line out and redraw it based on new information and new knowledge. And this is a really important aspect to being able to improve performance when there's a lot of ambiguity. So what does the team tell us, though? Well, we were able to do a lot more than we could before smart manufacturing got started, but we need more computing capability, we need more data storage capability, because the size of these data sets far exceeds what they can do in Excel, what they can do in JUMP. They need tools that allow them to do big data analysis. And they need to move to factorial experiments, and that analysis needs to be able to access lots of data. It's not something you can do hand-o-matic. So, we need these connected data streams. And for Corning, we're going to have our first cloud for manufacturing and a connected supply chain in 2017. We use cloud technology on the business side, but for manufacturing, there's a lot of reasons that it hasn't been done yet. Part of it is it's being developed. Part of it is those are our crown jewels you're putting out in the cloud, and the sensitivity of that is very high. So we're really looking forward to being able to bridge this capability gap that currently exists through our work with SESME. And this data looks straightforward. You say, well, this is just good process engineering. But the fact of the matter is that the data is so large that we can't use our good process engineering techniques of today in order to accomplish this process. So we're moving from gigabytes of data to terabytes of data per step, per piece. The data is complex. There's strong interactions between the processes. And we need to preserve the context, but we've got batch data, we've got continuous data, we got multiple site data. And so now you start to get a feel for This isn't something our systems of today handles very well. And we need to bridge that gap of Corning factory versus a non-Corning factory. We are going to have to make business commitments and build business relationships that are different than we do today. Sharing data is not something that our supply chain is used to doing. And we have to recognize the greater value that exists when we partner more than we do today, because I'm not going to drive your costs down because you're sharing information about what you're sending me. And I don't mean your costs. I'm not going to drive the price I'm willing to pay down because you're sharing data about what you're sending to me. And our suppliers need to be willing to do the same. This needs to be new business agreements that, at least for Corning, will be groundbreaking, and those will take some time in order to establish. And as I said, this can't be done with our legacy systems. So our team, and Dave Kuhn is here today with me, has been thinking about how do we bridge historical technology with bringing this capability of the future, particularly around cloud computing. And I think the most, actually I'd say the example that Jim Davis gave about riding a bike, then building a scooter, I should say building a bike, building a scooter, building a motorcycle, building, maybe it's a golf cart, it's got 4 wheels now, building an automobile, building a truck. This is a really good analogy because this process, this product needs something now. But I can't give them the Cadillac now because the Cadillac hasn't been built. We're still in the bicycle phase. And so giving them a bicycle and having a plan to get from a bicycle to a scooter to a motorcycle to a car is how we are accomplishing giving them value today on a trajectory that gets us to where we know we need to be in the future.